Hi friends, welcome back to Acharya Gurukul. Today's topic is wind load analysis, a solved example. In this video, I am going to explain introduction to wind load analysis, what are the various methods to be used for calculating the wind loads, procedure for calculating the wind loads, and a solved example. Wind is air in motion related to the surface of the earth. The primary cause of wind is traced to Earth's rotation and differences in terrestrial radiation. The wind generally blows horizontal to the ground at high speeds. The instrument which is used to measure the wind speed is anemometer. Wind speed has been considered that occurring at 10 meters height above the general ground level. As we know, wind is a random phenomenon load and all structures will experience dynamic oscillations due to fluctuation of winds. The terminology used in this video are as follows. Angle of attack or angle of incidence, which is represented by the symbol alpha. Angle in vertical plane between the direction of wind and a reference axis of the structure. Breadth, the symbol is used B. It means horizontal dimension of the building measured normal to the direction of the wind. Depth. Depth means the horizontal dimension of the building measured in the direction of the wind. Gust, a positive or negative departure of wind speed from its mean value, lasting for not more than say 2 minutes with the peak occurring over a specified interval of time. For example, 3 seconds. Peak gust. Peak gust or peak gust speed is the wind speed associated with the maximum value. Return period. It is the number of years, the reciprocal of which gives the probability of an extreme wind exceeding a given speed in 1 year. Suction. It means pressure less than the atmospheric or static pressure and is considered to act away from the surface. Solidity ratio. It is equal to the effective area, that is projected area of all individual elements of a frame normal to the wind direction divided by the area enclosed by the boundary of the frame normal to the wind direction. It is to be calculated for individual frames. Effective frontal area. The projected area of the structure normal to the direction of the wind. The methods used for calculating the wind load analysis are as follows. In general, there are 3 methods. One is pressure coefficient method, second force coefficient method, third gust factor method. Pressure coefficient method. In this method, it involves determining the pressure coefficients that is CPE and CPI associated with the various surfaces, shapes, and configurations of the structure exposed to the wind. The equation is used to calculate the wind load using the pressure coefficient method is as follows. F is equal to differences of internal pressure coefficient and external pressure coefficient multiplied with area and design wind pressure. Second, force coefficient method. In this method, it considers the shape, size, and orientation of the wind to the structure. The wind force acting on each direction, particularly X and Y perpendicular to the structure, is calculated by multiplying the force coefficient by the design wind pressure. The equation is used using force coefficient method is as follows. F is equal to CF into AE into design wind pressure. Gust factor method. It calculates the wind loads on structures considering the fluctuating nature of wind speed. It accounts for peak wind speeds or gusts that exceeds the mean wind speed. This approach involves multiplying the mean wind speed by a gust factor to determine the design wind speed. Gust factor method comes under the dynamic analysis. Now, when do we use dynamic analysis for calculating the wind loads? In general, the following guidelines may be used for wind-induced oscillations. Conditions. First condition is buildings and closed structures with a height to minimum lateral dimension ratio of more than about 5. Or second condition is buildings and structures whose natural frequency in the first mode is less than 1 Hz. If any building which satisfies either of the above condition shall be examined for the dynamic analysis of wind. Here a graph is plotted between time of the record in days from July 1983 to December 2005 versus wind speed in kmph. Now the below graph which represents the time of record in days for 1 year since July 1983 versus wind speed in kmph. Now, from this graph, the peaks values are taken, and based on the statistical analysis, they arrived the basic wind speed. So here on the right hand side, you see the table which represents the basic wind speeds for different cities or towns. The country is divided into 6 wind zones, which has the wind speeds are 33 meter per second, 39 meter per second, 44 meter per second, 45 meter per second, 50 meter per second, and 55 meter per second. And these wind speeds are calculated at 10-meter height above mean ground level with the 50-year return period. The basic wind speeds corresponds to a certain reference conditions. Hence, to account for various effects governing the design wind speed in any terrain conditions, modification factors are to be specified in the form of K1, K2, K3, and K4. K1 is risk level, K2 is terrain roughness and height of the structure, K3 is local topography, and K4 is importance factor for cyclonic region. Mathematically, it is represented as the product of VB, K1, K2, K3, and K4. As per IS 875 Part 3 2015, the K1 factor are given for various class of structures with the mean probable design life of the structures in years for various basic wind speeds. Here you can see the tabular column which represents various classes, all general buildings and structures, temporary sheds structures, those used during construction operations, buildings and structures presenting a low degree of hazard, importance buildings and structures such as hospitals, communication buildings, towers, and power plants, etc. The risk level is calculated. The values which are represented for K1 factor for various basic wind speeds and for various class of structures, these values are obtained using an equation K1 is equal to A minus B into ln of minus 1 by n into ln of 1 minus Pn, where A and B values are given in IS 875 code. Those are the coefficient values. A is equal to 88, B is equal to 20.5 for the wind speed of 47 meter per second, and n is equal to 25 years, Pn is equal to 0.63. So considering all these values and substitute in the equation, then will arrive K1 is equal to 0.908. Now you can see the value for 47 meter per second basic wind speed and 25 years mean probable design life of the structure, the value is 0.9. So like that, we calculate for each class of the structures and for various basic wind speeds. Second one, terrain roughness and height of the structure, that is K2. Selection of terrain categories shall be made with due regard to the effect of obstructions which constitutes the ground surface roughness. Here, as per IS 875 Part 3 2015, it is categorized as category 1, 2, 3, and 4. Category 0 represents the coastal area, category 1 represents flat terrain, 2 represents open terrain, 3 represents suburban area, 4 represents urban area. The values are given with respect to the height for various categories. Category 1 to 4, for 10 meters height, the value for category 1 is 1.05, for category 2 1, for category 3 0.91, for category 4 0.8. So that means for a particular height, as the terrain is moving from 1 to 4, the K2 value decreases. And if if I want to calculate the K2 factor for a height in between these two, then we have to do the interpolation, linear interpolation. For terrain roughness and height of the structure, for K2, the tabular column is given in IS 875 part 3. Third, local topography. The effect of topography is to accelerate wind near the summits of hills or crests or cliff and decelerate the wind in valleys or near foot of cliffs. The effect of topography will be significant at a site when upward slope is greater than 3 degrees and below that the value is taken as 1. The K3 with height above ground level and it is maximum near the ground and reducing to 1 at high levels. The equation is used for calculating the K3 factor. K3 is equal to 1 plus C into S, where C is equal to, if the angle that is theta value is in between 3 degrees to 17 degrees, then the factor C is used 1.2 into Z by L. And if it is more than 17 degrees, then C is equal to 0.36. Now here the diagram that represents the upward slope and downward slope with respect to the theta. Here the graphs are given for calculating the local topography for S factors for cliff and escarpments and S factors for ridge and hills. Next, K4, the importance factor for cyclonic region. In order to ensure greater safety of structures in this region, that is 60-kilometer wide on the east coast as well as on the Gujarat coast, the following values of K4 are stipulated. Structures of post-cyclonic importance for emergency services such as cyclone shelters, hospitals, schools, communication towers, etc. Then the K4 factor is used 1.3 region. Then the K4 factor is 1.3. For industrial structures, the K4 factor is 1.15. For all other structures, the K4 factor is 1. If the structure is not located in the cyclonic region, then we can use the K4 factor as 1. Next, wind pressure. The wind pressure at any height above mean ground level shall be obtained by the following relationship between wind pressure and wind speed. The equation is Pz is equal to 0.6 into Vz square, where Pz is wind pressure in Newton per meter square at height Z. Vz is equal to design wind speed in meter per second at height Z. The design wind pressure is calculated as follows. PD is equal to KD into KE into KC multiply with PZ. KD is wind directionality factor, KA is area averaging factor, KC is combination factor. The value of PD is, it should be greater than 0.7 into PZ. The factors are as follows. The description of the factors are as follows. KD, that is the wind directionality factor. For buildings, solid signs, open signs, lattice frameworks, and truss towers in triangular, square, and rectangular shapes. For truss towers, triangular, square, and rectangular shapes, the value of KD is taken as 0.9, and for circular shapes, the value of KD is taken as 1. For the cyclonic affected regions, also the factor KD shall be taken as 1. Area averaging factor. So this area averaging factor is calculated for overall structure, individual elements, plate type elements, and glass cladding. For overall structures, for evaluating loads on frames, the tributary area shall be taken as the center to center distance between frames multiplied by the individual panel dimension in the other direction together with overall pressure coefficients. For individual elements, for beam type of elements, purlins, etc., the tributary area shall be taken as the effective span multiplied by the spacing. For plate type of elements, the area of individual plates between supports is taken as the tributary area. For glass cladding, individual pan area of glass is a tributary area. For various tributary areas, the area averaging factor are as follows. The tributary, if the tributary area is less than or equal to 10 meters square, then the area averaging factor is 1. If the tributary area is 25 meters square, then the area averaging factor is 0.9. If the tributary area is more than 100 meters square, then the area averaging factor is 0.9. And if the tributary area is in between the values, then linear interpolation of intermediate values is to be permitted. Combination factor Kc. When taking wind loads on frames of clad buildings, it is reasonable to assume that the pressure or suction inside and outside of the structure shall not be fully correlated. Therefore, when taking the combined effect of the wind loads of the frame, the reduced factor Kc is equal to 0.9 may be used over the building's envelope when roof is subjected to pressure and internal pressure is suction or vice versa. The pressure coefficients. In order to determine the maximum in order to determine the maximum wind load on the building, the total load should be taken for each of the critical directions shown from all quadrants. Areas of high local suction, that is the negative pressure concentration, frequently occurs near the edges of the walls and roofs. Coefficients for the local effects should only be used for calculation of forces on these local areas affecting roof sheeting, glass panels, and individual cladding units. They shall not be used for calculating forces on entire structural elements such as roofs, walls, and structure as a whole. Wind load analysis on individual elements is calculated as F is equal to the differences of external pressure coefficient and internal pressure coefficient and multiply with the surface area of structural elements and design wind pressure. If the surface design pressure varies with height, the surface areas of the structural elements may be subdivided so that the specified pressures are taken over approximate areas. Internal pressure coefficient. Internal air pressure in a building depends upon the degree of permeability of cladding to the flow of air. The internal air pressure may be positive or negative depending on the direction of the flow of air in relation to the opening of the buildings. If the surface design pressure varies with height, the surface areas of the structural elements may be subdivided so that the specified pressures are taken over appropriate areas. Positive wind load indicates the force acting towards the structural element and negative away from it. Pressure coefficients given in different tables of IS 875 Part 3 2015 have been obtained from measurements on models in wind tunnels. For the structures that are not covered may be taken advice from the specialists in the particular subject. If the buildings in the buildings, the structural elements permits with an opening. If the opening is less than 5% of the wall area, then the internal pressure coefficient is taken as plus or minus 0.2. If the wall area, if the opening is in between 5% to 20% of the wall area, then the internal pressure coefficient is taken as plus or minus 0.5. If the opening if the opening is greater than 20% of the wall area, then internal pressure coefficient is taken as plus or minus 0.7. If the building have only one-sided opening, that means for B by D is greater than 1, for B by D is less than 1. If B by D is equal to 1, use average of these two values. Now here you see, this is the opening part, and in this direction the wind is acting. Now this is B and this is D, and the pressure coefficients are as follows, that is 0.8, and if the wind is acting in this direction, the pressure coefficient is 0.5. If the wind is acting in this direction, the pressure coefficient is 0.4. So these three cases are for B by D is greater than 1. Now the other case is B by D is less than 1. So for B by D is less than 1, if wind is acting in this direction, then the coefficient value is taken as 0.8. If the wind is acting in this direction, the pressure coefficient is 0.7. And if the wind is acting in this direction, the pressure coefficient is 0.3. External pressure coefficient. The mean pressure coefficient for walls of closed rectangular buildings with different aspect ratios is provided in tabular column below. Low pressure coefficients at the edges of the walls, which are relevant to the design of the structural walls and its connections to the supporting framework. Here you can see the tabular column, which represents the external pressure coefficients for A, B, C, and D. Now a diagram is explained in detail. This is the direction of the wind, that is 0 degrees, and the external pressure coefficients are as follows at A, B, C, and D. So A is equal to the external pressure coefficient at A is equal to plus 0.7, at B is equal to minus 0.2, at C and D the external pressure coefficients are minus 0.5. Now the same values you can see here, plus 0.7, minus 0.2, plus or minus 0.5 at C and D. Now this is the direction of the wind. Now the direction of the wind is 90 degrees. The coefficient values are at A minus 0.5, at B minus 0.5, at C 0.7, at D minus 0.2. Now you can see the similar values here, minus 0.5, minus 0.5, plus 0.7 and minus 0.2. So these coefficient values are for the building plan ratio, that is in between 1 to 1.5. In similar manner, the external pressure coefficients are given in IS 875 part 3 2015 for various structures like pitched roofs, monoslope roofs. In case of pitched roofs, the height and width are as follows, and the roof angle is like this. Similarly, for monoslope roofs also, height and width and the angle of the roof. Monoslope free roofs, freestanding double slope roofs, curved roofs, pitched roof of multi-span, top and bottom roofs of grandstand open 3 sides. So this is the case where you have in the stadiums. Next, wind load on a structure as a whole. The value of force coefficient applied to a building or structure as a whole, and when multiplied by the effective frontal area AE of the building or structure and by design wind pressure PD, gives the total wind load on the particular building or structure. F is calculated as CF, AE and PD. So CF is the force coefficient for the building, AE is the effective frontal area, and PD is the design wind pressure. Let us take an example to calculate the wind forces. So here is a plan and elevation. So this is the plan and this is the elevation with the bay width in along x direction as 6 meters and along y direction 5 meters. And the height of the structure is taken as 3 meters. The number of stories are G plus 6. Height of each story is 3 meters and the total height of the building is 21 meters. The plan dimension is 18 meters by 20 meter and the building is located in Pune. The basic wind speed for Pune is 39 meter per second and the design life of the building is 50 years. The design wind speed Vz is calculated as V1. The design wind speed Vz is calculated Vb, K1, K2, K3 and K4. So K1 is calculated using an equation which I discussed in the earlier slides. K2. So K2 is calculated for different heights. For up to 10 meters height, the K2 factor is 0.91. For 15 meters height, 0.97. 20 meters is 1.01 and 30 meters 1.06. K3 factor is taken as 1 as the topography is plain. The value of K4 factor is taken as 1 as the site location is under non-cyclonic region. The design wind speed that is Vz is equal to 39 into K2, because K2 is varies with respect to the height. So that's why right now we consider K2 only. Next, design wind pressure, which is calculated PD is equal to KD, KA, KC and PZ. The wind directionality factor KD is taken as 0.9 for rectangular buildings. Design wind pressure, area averaging factor Ka is calculated based on the tributary area. Now the tributary area for the building is calculated as column spacing multiplied with story height. So the column spacing is 6 meters and the story height is 3 meters. Hence 6 into 3 equal to 18 meters square, and the Ka is equal to 0.947 for 18 meters square. So here you have to do the interpolation between 10 meters and 25 meters. So that's why Ka is equal to 0.947 for 18 meters square. The combined effect of wind loads on the frame, a reduced factor of Ka. The combined effect of wind loads on the frame, a reduced factor of Kc equal to 0.9 may be used over the building envelope when roof is subjected to pressure and internal pressure is suction. Design wind pressure. The calculated design wind pressure PD is equal to 0.767 into PZ. The value of PD, however, shall not be taken as less than 0.7 PZ. Hence, the condition is satisfied. Wind pressure PZ at any height Z, the design wind speed in Newton per meter square at height Z is given by Pz is equal to 0.6 into Vz square, where Vz is equal to 39 into K2 as we calculated in the previous slides, which is equal to 912.6 into K2 square. And the PD value is 0.767 into Pz square, which is here. Multiply with substitute Pz value in this equation to arrive PD is equal to 700 K2 square. Now the design wind pressure at height Z are as follows. Height 10, 15, 20 and 30. The K2 parameter is 0.91, 0.97, 1.01 and 1.06. So these K2 parameters are taken from IS 875 part 3. So based on various heights and K2 parameter, the PD value is calculated. For 10 meters height, the PD value is 637 Newton per meter square. For 15, 679, 20, 707, 30, 742. The design wind load. The value of force coefficients applied to the building or structure as a whole, and when multiplying by the effective frontal area AE of the building or structure and by design wind pressure PD gives the total wind load on that particular building or structure. The equation is represented here. F is equal to CF into AE into PD. Here the value of A is equal to 18, which arrives the summation of 6 meters plus 6 meters and 6 meters. And B is equal to 20, which arrives from 5 plus 5 plus 5 plus 5. So this is the wind direction 0 degrees. And coming to the elevation, the total height of the structure is 21 meters. 3. Now calculate the aspect ratios. A by B, A is equal to 18 and B is equal to 20, which arrives 0.9. And H by B, H is equal to 21 and B is equal to 20, which arrives 1.05. Now, as per IS 875 part 3 2015, a graph is given with respect to A by B versus CF. So, A by B value is 0.9. So this represents 0.9, and CF value for A by B and H by B ratio is equal to 1. The value of CF is equal to 1.25. So that means the CF value is equal to 1.25. Now, the effective frontal area for 1 meter width may be taken as the center to center of the frame multiplied with 1 meter height. So here the center to center, the effective frontal area is calculated center to center of the frame. So In this case, the center to center of the frame is 5 meters, multiply with 1 meter, then it gives 5 meters square. Now substitute the values CF and AE in the equation F to arrive 6.25 PD. So the design wind loads is calculated as follows. For various heights, 10 meters, 15, 20 and 30. And the design loads are 6.25 into PD. So the PD value is, the PD value varies with respect to the height. That is 6.25 multiplied with 637. At 15 meters height, 6.25 into 679. At 20 meters, 6.25 into 707. At 30 meters, 6.25 into 742. Then finally we'll arrive the design wind loads are 3.98 kilonewton per meter, 4.24, 4.41, 4.63 at 10 meters, 15 meters, 20 meters and 30 meters respectively. Now, after arriving the wind load at various heights, now we have to distribute the wind loads along the height of the structure. So the tabular column is given with respect to the story height, story 1, 2, 3, 4, 5, 6 and 7. And the design forces values are given, with the distribution is represented here. So from 3 meters to 10 meters, the value is 0. From 0 meters to 10 meters, the value is 3.98 kilonewton per meter. And at 15 meters, 4.24 kilonewton per meter. At 20 meter, the value is 4.41. At 21 meter, the value is 4.63 kilonewton per meter. Now, we need the design force values at each story level. So that means at 21 meter, 18 meters, 15, 12, 9, 6, 3. At 21 meters, the value is 4.63. So 4.63 multiply with the story height, then we'll arrive 13.89 kilonewtons. Now, at 18 meters, if I want to calculate, then using a similar triangle principle to arrive the value at 18 meters. So at 18 meters, the value is 4.342 kilonewton per meter. Multiply with the story height, then we'll arrive 13.026 kilonewtons. Similarly, at 15 meters, the value is 4.24 multiplied with 3, which is equal to 12.72 kilonewtons. At 12 meters, the value 4.048 kilonewton per meter multiplied with 3 meter will get 12.252 kilonewtons. At 9 meter, 6 meter and 3 meter, the value is constant. So that's why the design force is calculated as 3.98 multiplied with 3, then we'll get 11.94 kilonewtons. So this 11.94 kilonewtons is same for 1 story, 2 story and 3 story. The calculated design wind loads are distributed like this. Here we can see the diagram that represents the design wind loads from this video are the design wind pressure, the wind load on individual members, wind load on a structure as a whole, and the distribution of the wind loads. Thank you. Jai Hind.